All right, inverses. We're going to first take a look at just how to find an inverse today. And then, because you want to be able to have inverses, because remember, those are things that will cancel each other out. And so if you're having a problem, sometimes taking the inverse will help you cancel that out, and you'll be left with something a little bit easier to deal with. So it would be helpful if we know how to find an inverse. So here it says to determine an inverse, we would switch x and y and then solve for y. Okay? And so the first one that we have here, you might say, it says determine the inverse for f of x equals x to the third, and your first comment might be, where's y? But remember, f of x means it's a function. We can replace that with y if we choose to. Okay, so it is really y equals x to the third. Now, notation for inverses here would be f to the negative 1 of x, okay, or now we could say y to the negative 1 of x. It does not mean necessarily 1 over y or 1 over f of x. It's just a notation within this problem to show us that that's the inverse. Okay? So if we are to start with y equals x to the third, this rule up here says to switch x and y. And what that means is switch the location. Don't move anything else, just where x and y are. Now, what if you have multiple x's over there? Well, you basically replace them all with y and go on your way. So this one, what we're going to do is, this was a y right here, so we're going to replace it with x. That was an x right there, so we're going to replace it with y. But there's still a third power there, correct? And now what we're going to do is, because a lot of times we like to look at things as y equals, what we're going to do is try and get y all by itself then. But we're going to try and get y all by itself at that step. And how can we get y all by itself at that step? Yes? The cube root both sides, exactly. And let's change the color on that. Because over here, and I don't know, again, I think it's getting fewer and fewer those that had me for Algebra 2, but they kind of call that it houseifies because it cancels. Okay? And so here's your y equals the cube root of x. Agreed? And now if we wanted to, seeing we started with this, what we'll normally do is put that little negative 1 on that one so that we know that these two, when working together, are inverses of each other. That's the only reason we put that little notation on there. Because otherwise it just looks like two y's in this problem, correct? And now what I'm going to do is I'm going to write that over here on the other board so that we can, and you don't have to get your graphing calculators out, I just want to show you something. And while I'm getting that ready, maybe think, we've done this recently. When have we switched x and y? It was one of our symmetry tests. So while I'm bringing up the calculator, see if you can remember which symmetry test that was. Okay? So y equals, we're just going to take a look at these graphs because I think I gave you a little graph off to the side, right? So y equals x to the third. Should you be able to do that one relatively easily? Why should you be able to do that one relatively easily? It's one of your parent graphs, right? You should be able to put that one in there fairly well. Now, how about the cube root of x? You might not be able to do that one very well. So let's show, one of the reasons I want to do this is show you that cube root is on here, all right? And also, there is another way you could do it. So if you go under math, you can see that cube root is right here at number 4, right? Number 5 is saying any root. So you type a number in first, and then you hit 5, and then that number takes the place of x. So you could do the 5th root or 6th root or any of those. But third root is actually one of them, so we'll do that. Third root of x is apparently the inverse, correct? Okay. So what it's going to do first is it'll graph y1, and then it'll graph y2. Okay? So let's see what it looks like. So again, this is the one you should know, right? There's x to the third, and here comes the cube root of x. Okay? Did anybody remember, where did we switch x and y? Which symmetry test was that? Yes? Oh, okay. Yeah, it was for the line symmetry of y equals x. What I'm going to do right now is I'm going to go back in and I'm just going to put y equals x in there just so you can see it. And there it comes. Okay. Now I've been having some troubles with this. So if you agree that this point goes right out to that point, right? Now these in here are a little harder to see, so I'll zoom in a second. Okay, but you see there is that reflection over that. So the inverse is, it is just a reflection over the line y equals x. Let's zoom in. Look at the inside there. So there's your x to the third, and here comes your cube root. Okay. And there goes y equals x. So do you agree that that does have symmetry with respect to the line y equals x? Okay. And that's what inverses should do. Okay, so that's kind of neat. Okay, would anybody like me to zoom back out so you can draw yourself a little sketch there? I can if you'd like. We'll go to zoom standard. Again, there's your x to the third, and here comes the cube root. So any questions on the first one? No? On the second one, you have x plus 4 squared minus 6. Could you please sketch that for me real quick while I'm clearing these out? Because that is from your parent graphs. You should be able to sketch that one. I'm just going to clear these out because we're going to need them in a second. And we'll just leave that up. Okay, so here's the one I was talking about. X plus 4 squared and then minus 6. All right, what's the parent graph? X squared. And what should I do to x squared according to the transformations that we said earlier this year? Left 4, right, because of that one, and down 6. So left 4, down 6. Now you actually have graph paper on there, right? And should I reflect it? No, so this should open up, down, sideways, what? Up. Okay. So in general, something like that. Agreed? Okay. So now let's go ahead and find the inverse. And what is it that we do to locate the actual inverse? Is switch any x's and y's, right? So here I see a y. So instead of y, I'm going to put x equals. There's an x. So instead of that, I will put y. Well, this one's going to take a little bit more algebra than the first one. Because what did we do at this point? We just didn't switch them. Okay. Now, if we were on GeoGebra, I know that we could graph that, or I think some of the calculators will graph x equals. Okay. But for right now, I mean, we could by hand, but normally we want them to be y equals, right? So how would we go about that? Well, what probably would be our first move? What do you think? We could square root, but remember, if you square root, you have to do it to the entire side. I would move the 6 first, probably. Yeah, don't FOIL that. No, don't do that. Because all that does is introduce another y, so let's not do that. So x plus 6 equals, and I think you'll see why we don't want to FOIL here in just a second. Now we can go to what one of the students said earlier, which was to get rid of the square, we can square root. The reason I didn't want to square root earlier is I would have had to have square rooted all of that right side. So that negative 6 would have been in there as well. And then square root this side. Okay? And so what happens here, the housifies again, right? So y plus 4 now what? We want to get y by itself. Yeah, subtract 4. Does the subtract 4 go inside this radical, stay outside? How's that all work? Yeah, it stays outside, right? Okay, so there's our inverse. Again, sometimes you could put that little negative 1 power on it so you know it's your inverse, because this is what I started with. Do we also know how to graph that one by hand? Yeah, that's also one of your parent graphs. Right? It's the square root of x. And what should I do to that square root of x? Left 6 and down 4. Again, this is by hand. I missed that one a little bit. But wait a minute, the square root of x only has the top half, right? Boy, that sure doesn't look like it's following the rules of the first one. Why is it plus or minus? Yeah. Who decided to take the square root in this algebra? We did, correct? We decided to take the square root. And so do we know if it's the positive or negative, which one we're supposed to use? No, so that's when we have to put both of it. And what does that negative out front do? It gives you the reflection of it, correct? So it'll also give me that one. Okay. Okay, without the positive negative, we wouldn't have, this wouldn't look right, would it? Okay. And now what I have over here, and we can go to the graphing calculator if you want to see it again, but I have it over here. and there's your line. Okay. So do you agree? That is definitely a reflection again. Okay. So it's one easy way to check when you graph it. If it's not a reflection over the line y equals x, then you don't have the inverse. And if I didn't have the positive and negative here, I didn't have the entire inverse. Okay. Any questions so far about inverses? This one is relying on your previous knowledge of a function test. So we'll go up here. Do you remember if I gave you a function, say in Algebra 2, and let's say this was your function, if I wanted to know if that graph was a function, you did the vertical line test? And if it only hit it once, you were good, right? If it hit it twice, it was no good? That's because every x value should only give you one y value in return, right? Kind of that function as a generator. If you put an x value in, it should only give you one y value in result. And so like this, that's good, that's good. But if I gave you that as the actual graph, vertical line test fails, correct? Well, so now what you can do, what I want to know is how about the inverse of that graph? So you got two options. Your two options are you can actually reflect this over the line y equals x, and so it would end up being something like that, correct? If I reflected over the line y equals x, I would end up with something similar to that, and do the vertical line test on that. And so the inverse of this graph, the one that parabola I gave you, the inverse is not a function, correct? How about the original? Is the original a function? Yes, but its inverse is not. So that's one way to do it, right? But do you agree that some functions are going to be hard to reflect in your head or be able to see it, right? And so what you can do is let's take that vertical line and reflect that and test it that way. If you reflect a vertical line, what do you get? A horizontal line, right? So let's just test these by horizontal line. So when you do horizontal line, you're testing if its inverse is a function. So horizontal line says that the inverse of this one is not a function, right? How about the original, though? Is this original a function? Yes. How about this original? Is this original a function? How about, again, that's vertical line test, right? How about its inverse? How do you test that? Okay, are there any places it fails? Okay, it does look close right there. Somebody said the x-axis, but it does keep creeping up very slowly and keep going. But that's a great observation. That's one place that was potentially a problem, right? But it does keep creeping up. So the original is good, and its inverse is good. Okay. How about this one? The original? Is it a function? The original. How about the inverse? No, right? Original, you do vertical. Inverse, you do horizontal. Okay. That's just a quick way to do it. If you want to reflect it, go right ahead. Reflect it over the line y equals x and test it. But I think it's just way quicker just to do the horizontal line test. Okay. So how do you test the original? It's a vertical line test. How do you test the inverse? Horizontal. And if you don't have that written down somewhere on your notes, I have no idea why you don't. Okay, because that would be very easy, a very quick test for you to find out. Any questions?